teach him exceptions. We'll do the notes again. All right. So right now we are dealing with cerium, and cerium has this electron configuration. What was I saying? I lost myself.
How do you put it on
Oh, you checked. All right. Xenon is 54 electrons. Is that right? By writing xenon in square brackets, we've accounted for 54 electrons. 54 plus 2 is 56, 57, 58. That's how you can double check that you've written out all the electrons for the given element. Is that clear? Okay. Now, when you try and figure out what element it is, let me see. Where is this paper?
Ms.Geeta, for like the exceptions,
Yeah.
do it only when it's like right before the fill.
Right before the fully filled and the half filled. We'll take notes on it. All right? We'll take a little bit more notes on it. Let's see. Can you turn to the back page of this? Can you turn to the back page? All right. You have the homework sheet, right? You should try writing all electron configurations at home. All right, next class there's going to be a quiz on this. Writing electron configuration, drawing orbital diagram, finding the mistakes. There'll be a quiz on all this next class. All right? Let's look at this electron configuration. And given the electron configuration, you're asked to find out what element it is. Is that right? Now, kids will often make the mistake of looking at F11 and saying, oh, I will find my element because it ends in F11. Is that right? For most of the time, it will work. For instance, if you go to this one, it is 3p4, 1, 2, 3, 4. The given element is sulfur. It's a quick and an easy method. But remember, there are many exceptions to writing electron configurations. Did you understand what I did there? Everybody followed what I did there? Any questions on that? But when you come to this, you will incorrectly choose the element. Because if I do F11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, what element would I choose? Fermium. But the given element is not fermium because what is the right way to figure out the element? You count. 86 plus 2 is 88. 88 plus 11 is 99, which makes it what element? Einsteinium. Do you understand? So because of the exceptions in writing electron configurations, you should actually count out the electrons in order to figure out what element it is. Does that make sense? Otherwise, some of the examples could trip you. Most of the time it works, all right? Especially when you're higher up in the periodic table. When you start filling in the f orbitals, it's better to count because there are exceptions, all right?
You could just count up the exponents.
Yeah, count up the exponents. Don't look at the last configuration is what I'm saying. Look, don't look at F11 and say this was fermium. You'll trip. Okay? Now, the next one is the rules. All right? When you take a quiz, the three rules, the off-course rule, the Pauli's rule, and the Harm's rule are really, really important. All right? They always love to test you on that. What are some of the mistakes in this worksheet? Can you have a noble gas as its own abbreviated noble gas configuration? Can you do that? No, xenon should start with what? Should start with krypton and it should follow along. After krypton, what is it? It's 5s2, 4d10, 5p6. Okay? And here they have written the element Ra instead of the element Rn. So you should know which rule is being violated. So for that, all right, try these examples at home. I think I have the answer key up on Blackboard. Make sure you're practicing, all right? Practicing these problems. Now, let's go to this worksheet that you have. How long is this class till? I have like 40 minutes, right? So, you should know the 3 rules, alright? And you should be very good at figuring out which rule is being violated where, alright? So, what is the problem with this worksheet? After 1s2, 2s2, 2p6, what should you fill in next? After 2p6, what do you fill? You should fill 3s2. Alright? So 3s2 is not filled. Is that right? You can't find 3s2. So which rule is being violated here? If you don't fill 3s2 and you jump, the off-bus rule, lower energy, is not getting filled. And so you are violating off-bus rule. Alright? The violation is off-bus principle. And what is the correct electron configuration? 1s2, 2s2, 2p6, 3s2, 3p1. Is that correct? Now, if you look at the next one, 1s2, what should it be? 2s2. Instead, what do you see? You see 2s3. Here is where the mistake lies. Why can't you put 3 electrons inside an orbital? What rule is being violated? Pauli's exclusion principle, which states that only 2 electrons can reside in an orbital and they should have opposite spins. Is that right? So the correct electron configuration will be 1s2, 2s2, 2p1. What about the next electron configuration? Which rule is being violated in the next one? They skipped 3s2. So that's a violation of off-bus rule. Now you don't have a name for the next one. There isn't any rule. You can just say half-filled and fully filled electron configurations are more stable. This is the copper that we did. Is that right? You cannot have 4s2 3d9. What should be the electron? You should say fully filled is more stable. Fully filled is more stable. Alright? And so you would write argon 4s1 3d10. Right? For the next one, which rule is being violated if they have the same spin? Pauli's rule? Pauli's rule says they should have opposite spins, right? For the next one, what rule is being violated? Whose rule is being violated? Off-bus. Now let's come down to carbon. Alright? When you come down to carbon, it says 2px2. How do you interpret 2px2? It means that when you have your boxes, alright, it means that there is 2 in the first box, there is 2 in the second box, and when you have P, both of them are in the same box because this stands for Px, this stands for Py, this stands for Pz. If you put both of them in the same box in P, which rule is being violated? Hund's rule, right? Hund's rule is being violated. This is a violation of Hund's rule, which states that it should be 1s2, 2s2, 2px1, 2py1. Does that make sense? One in each box. Does that make sense, guys? Do you understand it? Yes, no? Any questions? Do the remainder of the worksheet and learn your problems. Okay. Yeah.
Can you give another example of breaking Hund's rule?
Hund's rule. All right. Let's see if there is one more example on this paper. Hund's rule is, okay, can I ask this configuration? If I put 2 in this box That's my 1s. I put 2 in my next box. That is 2s. And I put one like this and one like this. Is my electron configuration in violation of Hund's rule?
No, you're not going to say. Actually, no.
Is it in violation of Hund's rule?
No, isn't it in violation of the
Is it in violation of Hofbauer's rule?
It's got a lower energy orbital though.
Is it in violation of any rule or is it perfect? Is it violating Hofbauer's rule? Is it violating Hund's rule? What is it?
Nothing.
The electron configuration is perfect.
Because all the
They are equal energy orbitals and they are occupying one each. They have the same spin. It doesn't matter whether I put it in X and Y first or X and Z first. The orientation doesn't matter. They are equal energy orbitals. None of the rules are being violated in this example. Yes or no? Yes or no? Do we follow? Alright? So, you could get asked questions like this. You have to know your rules really, really well. Alright? Now, let's move to what are orbital diagrams. I don't know, on the back of this sheet is orbital diagrams? Good. Alright, go to this sheet. Yes. The 3 boxes. So, I prefer to call this 2px. This is the 2py. And that's the 2pz. Remember, the p orbitals are the 3 orbitals that are the dumbbell-shaped orbitals. Remember this? Remember them? And I can have them go into any one of the 3. They're equal energy orbitals, and they can go into any one of them. Okay? Now, if they ask you to draw the orbital diagram, alright? You know how you started this unit with the orbital diagram being given to you and you wrote out the electron configuration? Isn't that right? Now all the support is being taken away from you and you are told, well, write the electron configuration, draw the orbital diagram. What are you asked to do? Draw the orbital diagram for, let's say, carbon. Alright? Draw the orbital diagram. If they ask you to draw the orbital diagram, what are they asking you to do? What do orbital diagrams mean? Orbital diagrams means boxes and arrows. Know the difference between electron configuration and orbital diagram. What is the difference? Alright? Now, electron configuration is when I write 1s2, 2s2, 2p2. Alright? So, I need to draw the orbital diagram for carbon. What do I need first? I need my electron configuration. I know carbon's electron configuration is 1s2, 2s2, 2p2. Is that right? Once I know the electron configuration, now I am very comfortable drawing the orbital diagram. Because how many boxes will I draw if it is an s orbital? How many boxes do I draw? One. How many boxes will I draw if it is a p orbital? How many boxes will I draw if it is a d orbital? 5. And how many will I draw if it is an f? 7. And so you should know that. So this is my 1s orbital and I will put my 2 electrons in. Now what am I doing? Now I am drawing the orbital diagram for carbon. Is that clear? And then I draw my 2s and I put an up and a down arrow. And then I draw my 2p. How many boxes? 3 boxes. How will I put the 2 electrons in the 2p boxes? 1 each. Is that right? 1 each. Can I double up? You will get the answer wrong. Do you understand? Do you understand what is orbital diagram and what is electron configuration? Now you'll be asked to draw, and that's based on writing out the electron configuration. Now what I want you to do is, whatever we have learned so far, let's go and take notes and go to extension notes on electron configuration. Okay. Where is tantalum on the periodic table? Number 73. Tantalum is 73. Alright? I need you students to write out the complete electron configuration of tantalum. Go.
Unabbreviated.
Unabbreviated. It says complete and noble gas. I need you to do your own work and check with my answers. How are you going to learn if you just copy off of what I do? Do your own work and then check. Are you getting the same answer that I am? Am I correct or have I made a mistake? Sometimes I'll purposely make a mistake. You should know to catch that. Am I right? Am I right in writing out the electron configuration for tantalum? Yes or no? Did I make a mistake anywhere?
What about the
Nobody's answering.
5D one? Okay, wait, she added on after. She like put it in, she did like one.
Yes, Harry. Is everything okay? Did I make a mistake? Sometimes I'll purposely make a mistake.
Oh, she did. Okay.
I did?
Wait, so like you have the 5D1. Would you put that before?
Yeah, I would like to combine. Don't do 5D1 for F14, 5D2. That's
Okay.
like, do combine them. Alright? Now, I like how your wheels are turning in your head. Alright. So we are good with writing the complete and the abbreviated noble gas configuration. We know how to jump into the F and come back to the D. Is that right? Okay. Yes. I see they are getting it. Alright? You will get such configurations on your test. Now, the next thing is you need to know the shapes of the orbitals. What is the shape of an S orbital? It's a sphere, spherical. What is the shape of a P orbital? It's a dumbbell. What is the shape of a D orbital? It's a flower petal. And the F is complex, alright? We really don't need to label it. Now, let us come to chromium, alright? So where is chromium located? You know how we did copper as an exception? Did we say copper was, Hatyan, listen, did we say copper was just before the last filled orbital, so it will pull it out from 4s? Let's look at chromium. How many in the d orbital total? 10. 1, 2, 3, 4. What is a half-filled d orbital?
5.
D5. Just before the half fill. Is that right?
Yeah.
Those elements that are just before the half fill and those that are just before the fully filled will become exceptions to electron configuration. So if I were to write chromium, I would write fill in just the 4s and the 3d orbitals. So they want us to do the noble gas configuration. So the noble gas configuration for chromium would be, if you did it naturally, 4s2, 3d4. Is that right? But is chromium an exception? Chromium is an exception. So how does this electron configuration change? What does it become? 4s1, 3d5. All right? 3d5. Now, they are not asking us for the electron configuration. They actually want you to depict the orbitals. So, I'm going to draw the orbital. How many orbitals do I draw for S? And how many do I draw for D? 5. So, 1, 2, 3, 4. 1, 2, 3, 4, 5. So, that's my 4S. That's my 3D. Alright? And my electron is going to be like this. Is that right? Is that how my orbitals 4s and 3d are going to look for chromium? Are we good?
Wait, Ms.Geeta, is that only for the D and the F ones, not the P?
P doesn't have that. Like the exceptions, the pulling out doesn't happen between the S and the P. And what is the reason for that? I don't know. I don't remember when I gave you this worksheet. But do you remember that when we did the Bohr model, you had the 1s energy level. The 2s is quite high, and then you have the 2p as the next energy level. Then comes the 3s. Now the energy difference becomes lower and lower between the higher energy orbitals. Is that right? So when you come to, this is the 3s and the 3p, there is still a significant difference in energy. But when you start going up, it becomes the 4s, and then what is the next energy level that fills in? It is the 3d, after which what fills in? 4p. So the energy difference is so small that the electron is, we can pull the electron out and make it half filled. Does that make sense? Do you understand it? Whereas such a transition is not possible here, where there's a large energy jump. Here it's like almost negligible. Does that make sense? So it's very relevant when you come into the d orbitals, and that's why when you go into writing F, elements that are in the F block, we are only going to do one type of exception. That is the half filled and the fully filled. Is that right? You cannot write the electron configuration for chromium as 4s2, 3d4. That will be wrong. You have to write it as 4s1, 3d5. And if you go to copper, you need to write out the electron configuration as 4s1, 3d10. Is that right? There are many more exceptions when you come to the F orbital. We will not touch those exceptions. And why do you have so many exceptions? Because the energy levels are now so close to each other that they overlap, and whatever offers the element stability, that is the electron configuration it will have. But we will test you on half-filled and fully filled electron configuration. Is that clear? Okay. So, which are the ones you need to know are the exceptions to the rule? All right. So, This is 1, 2, 3, 4. This is the fourth one. So the fourth one will all have the D5 instead of the D4. Is that right? Do we understand that? Because they will pull one from the F. Similarly, the ninth, copper, silver, and gold will be D10 and not D9. Do you understand? Those elements, if you're tested on those elements, make sure you're writing out the correct electron configuration for those elements. All right?
When we know, do we have to memorize?
You have to know. You have to locate the element and you have to know. I will just throw it in with the random elements. You have to keep in mind, oh, this is the half-filled one, so I better write the electron configuration correctly. That's all. And copper has the electron configuration. We already did copper. Is that right? Let's do molybdenum. Molybdenum, I'm going to do the abbreviated noble gas configuration. Molybdenum is getting pulled out from krypton. And then I have 5s1, 4d5 will be the electron configuration for molybdenum. Do you understand it? Yes or no? Okay.
Good morning. Teachers, please pardon the interruption as we begin our morning announcement. Please make sure TV in your room is on channel 6 at this time. Students, please stand for the Pledge of Allegiance. I pledge allegiance to the flag of the United States of